2 appears alone in the off diagonal element. So at least you should be able to tell what gamma 2 is. Yeah. So use this. So, yeah, so gamma 2 is the second derivative of psi with respect to gamma theta 1 and theta 2, like you said. What's your name? Miguel. What about gamma 1? Or what about kappa? That might be the next simplest thing. So how do you separate kappa and gamma 1? Because they are appearing together. So do you have an expression for kappa? Yeah, that's good. And gamma 1? Yeah, that's good. But how did you solve it? Did you take A11, A22 separately, or? Yeah. So you can start with the trace of the matrix. So trace of this matrix would mean you add these two. So you get 2 times 1 minus kappa. The gamma 1 cancels. So we've already separated gamma 1 and kappa here. And if you take the trace of this, so you need to evaluate this expression for I and j equals 1, I and j equals 2. So you'll get it as 1 minus del square psi theta 1 square. So that's I and j equal to 1. So you get 2 minus so the 2 cancels, and then you can get kappa as so this is independent of your choice of coordinates. So whether you choose theta 1 and theta 2 in this direction or theta 1 and theta 2 in this direction, this combination will stay the same. And there's a more compact notation for this. It's given by the gradient square, or it's called the Laplacian operator.
Shouldn't it be minus between the derivatives? No, on the upper line.
Here?
On the right. The right.
Oh yeah. Yes, thanks. So you get something like this. You probably have not taken electrodynamics, but this is very close to what you get in electrodynamics, that you will say that the Laplacian or the gradient square of the voltage will be the charge density times. So this is known as Poisson equation. It is essentially the electrostatics that you know written in a more compact form, and this equation is very similar to this. So if you do enough fields in physics, you will see that one field can actually be mapped to another field. So that's the thing. And we still have gamma 1. So now that you found out kappa, you can just take one of them, say A11. Is it visible if I write here? Yeah. So A11 will be 1 minus kappa minus, I will take, okay, gamma 1. And so we already know what kappa is. It is 1 minus and A11 from this expression is so you can cancel the 1, you can bring gamma 1 to this side, everything else to other side, and you will get gamma 1 to be half So in terms of this, so you can see that so many quantities can all be written in terms of this one lensing potential psi. So if I give you psi, all you have to do is to do appropriate differentiation, and you end up with many different quantities. So kappa is half So since kappa and gamma 1 have this prefactor of half in the front, let me also do the same to gamma 2 by multiplying and dividing by 2. So now they all look pretty much the same. So if you look at this structure where it says something squared minus something squared, and here's a cross product. Does it remember you of anything? Does it look familiar to you? So if you consider a complex number z as x plus iy, I will also call this as r and e. I'll write the complex number in both Cartesian xy and polar form. What about the square of this number? What is it in Cartesian form? So what happens if you just square this complex number? So the polar form is easy, right? It's just r squared e power I25. In the Cartesian form, you get an x times x squared. You get an iy times an iy. But I times I is minus 1. So you get this. And then you have the cross terms. I times xy, I times yx. You get this. So gamma 1 looks like this, except with a half in the front. But it's something squared. It's the derivative with respect to theta squared minus derivative with respect to theta 2 squared, and gamma 2 is like the cross derivatives theta 1 and theta 2, just like x and y. So compare x with 1 by square root. So there's an equivalence between complex numbers and this gammas. So the gammas are what we call as shear or lensing shear, and this is what you can measure from the data. So if you look at telescopes, you look at many galaxies, and we will see how exactly to get the shear on Wednesday, but this is measurable, and once you get the gamma 1 and gamma 2, you can also get the kappa. So because you can get what the psi is, and you can, from psi, the lensing potential, you get kappa. And kappa is also given by this, the sigma over sigma critical. Sigma was the mass density integrated along the line of sight. So which means if you get kappa, you get this quantity. The sigma criticals are essentially some constants. So if you get this sigma, which also means you can get an estimate of how mass is distributed. So this is essentially the principle. So this is the observable. The gamma ones are observable, and from there you trace back all these steps, and you can get the distribution. So this is how you calculate mass from weak lensing or lensing in general. So this is the main principle. The sigma critical here, so these are fundamental constants. These are never going to change. But these ones depend on distances. So you need to know where the source is, where the lens is. Now, so estimating this distance to source and lens is done by calculating the redshift of the sources and lens in cosmological surveys. So the Hubble's law would say that the velocity with which the galaxy is moving away from us is proportional to the distance. The proportionality constant is the Hubble's constant. And since the galaxies are moving away from us, the light that it emits are also redshifted. So by calculating how much the redshifts are, you can calculate with what velocity it is moving away from us. And you can use, if you know the Hubble's constant, you can estimate how far these lenses and the sources are. So once you know these distances, you have sigma critical, you can measure kappa, you have sigma, and you have sigma, you don't quite have the rho, but you at least have an idea about how it is distributed. You get some information about the mass distribution. So that is So that is how we estimate the masses. So we'll do a more concrete example of this. It is so we'll take an example model called singular isothermal sphere. So can I erase the board fully? So this idea about lensing, so we'll calculate a lensing potential for this object explicitly, and then we will calculate all the kappa, gamma 1 and gamma 2 parameters. So the singular isothermal sphere is essentially a very simple model for a sphere. It's somewhat unphysical, but it seems to be working very well in practice. So what this says is, if you consider a self-gravitating system, so if you take a gas under its own gravity, it's collapsing. But if you also assume that it is isothermal everywhere, that is, it has all same temperatures throughout, then you get a density profile given by this. So we can motivate this form in many ways. So this captures the dark matter profile pretty well. So remember the rotation curves that I showed even in the video. So the spiral galaxies were rotating, and then if you calculate the distance from the center, and this is the velocity of rotation, it went something like this. So if you assume that all the mass is concentrated at the center and an object is rotating this with a velocity v, then this would mean that the gravitational force of attraction, which is gmm over r square, is what is providing the centripetal force for this object to go around. So this would be mv square over r. And cancel this m. So pretty much in no gravitational problem will this small m, this mass of the lighter object will remain. And you get v square is proportional to 1 over r. So, or v is proportional to 1 over square root of r. So this is what you would have expected if everything is concentrated at the center, but you don't get that. You get pretty much a constant to a very large distance, even outside, like till the very last, to the outermost star you can see. So from experiments what you get is v does not go down this way, it stays pretty much constant, so it's r power 0. And so which means m is not all concentrated in the center, but if you calculate all the mass within a radius r in the sphere, it will go something as so I'm assuming that this lens is spherically symmetric. So the density can only depend on the radius, how far it is from the center, and not the direction. This is the area of this surface, the surface area of a sphere with radius r. So I've just divided up the sphere into many shells. The volume of each shell is 4 pi r square dr, and the density there is rho of r, and this will give you what is the mass enclosed in in a sphere of radius r. Now, for V to not go as 1 over square root of r, but to go as r power 0, which means it is essentially a constant with respect to r, how should rho of r go like, or how should m of r be like? So if you do this equation, so I'm going to change this to capital R. So you don't want V to go as this, but you want to go as V, or V going as r power 0. So how should m be? So this m is m. So this is everything that is inside this sphere. So that is what I meant by m lesser than or equal to r. So that's so clearly, if it is a point mass, it has to go this way, which means it is not a point mass, it is distributed. And at larger radii you go, the mass might increase, which is why I am explicitly putting the size of the sphere in here. So if this has to go as r power 0, then m has to be proportional to r itself. So that this gm over r square will go as 1 by r, and that is same as v square by r, and v will not have any r dependence. Is this clear? So all that I am saying is, if this was true, this would mean g over r square will have a function dependence that goes as r power minus 1. But we also know that this is same as v square by r, which goes as r power minus 1, which means v square is independent of r. So independent of r is what I meant by r power 0. So if the mass within a sphere of radius r should go as r, then that means, what does it tell about rho of r? How do you make this quantity go proportional to the radius r? You already have the hint there. Do you understand the question? So I want this quantity, which is a function of r, to be linear in r. What does that mean for the density, rho of little r? How should rho of little r be as a function of r for this to have a linear dependence in r? The answer is already there. Yeah. And this, it's not r cubed. No. Yeah. So if rho of r is some constant divided by r square, then the r square here cancels. You get k r square 4 pi r square dr. So the r square cancels. You get 4 pi k integral dr. This is exactly what we wanted, right? So m the mass within a sphere of radius r goes proportional to the radius r itself if the density goes as 1 over r square. So the farther away you get from the center of the sphere, the density should reduce in this manner. Then you are guaranteed to have a rotation curve which is flat, that is, it does not die down as a function of r. So that's one of the motivation. So it's an empirically or experimentally motivated model to have a density that goes as 1 over r square, and the constants there are such that it can also correspond to some to a gas of some temperature, but that's not very important. It is this functional dependence that is very, very important. So okay, so we will start with this density profile. So this is the density profile that we have, rho as a function of r. The first thing that we need to do is to estimate sigma. So can you do this integral over the line of sight coordinate? So that's the surface mass density.
The surface mass density?
Yes. So which is defined by this integral. So you have this sphere with a density profile like this. So the farther away you go, the less dense it becomes. Say I put this sphere very, very far away from you. So you don't see how it is distributed along the line of sight, but you can see the width. So you can see the width in the 2 dimensions of the sky, and that is what lensing will measure. So it will not tell you anything about how it is distributed along the line of sight. So that is not important to us. So we have to do this integral. So for this, yes. So if you do this, so if you integrate this, you will get this. So we will do this integration. So this is the center. If you take a point at a distance r, the density there is some constant. We'll just call that k. And so let's assume that we are the observers here, and this is the plane of the sky. We have to integrate, and this is a sphere, so we have to integrate along this line of sight. So we will integrate in this direction, and again the convention is to use chi1 here, chi2 goes, so now I will use this for R3, and chi2 goes. So the board is the plane of chi1 and chi2, and R3 goes into the board, and we are going to integrate over R3. So I can write R square then as chi1 square plus chi2 square plus R3 squared. So I just used Pythagoras theorem to express the distance, square of this distance in terms of the individual components, and I will make this explicit. So you can assume that this, you can assume that we are going to integrate from minus infinity to infinity, because as you go very, very far away from this object, the density is very low. It goes as 1 over r square. So I don't really have to know the size of this object. I'm just going to assume that we can do this integration of r3 . So again, this has the same substitution as before. So you can do this substitution and then you can use this identity. So if you do this integration, then you will get k divided by with a pi. So I'm using chi vector and chi1 and chi2 interchangeably, but they are the same. It has the same meaning. And if k, this constant k has this particular form, then you get the expression on the right. So it is just about doing this integral in a third dimension. Okay, so here we are doing this kind of for modeling by saying we will consider a density profile and let's go through these steps one by one. So we started with the 3-dimensional density. Now we've gotten the 2-dimensional density. The next thing that we will do is the kappa. Okay. So then the convergence of this or the kappa of this would mean, let me use a different one. And I will use this k as that particular constant. You can do the simplification. And again, so the surface mass density or the 2-dimensional density or the kappa goes inversely proportional to the 2-dimensional vector, the chi, or it goes inversely proportional to the angular position, the theta itself. So remember that. So since this is so forgetting all the constants, you will get this. So this essentially tells that the farther away that you look in the sky from the center of this lens, the smaller the excess mass density, or the smaller the surface mass density that you will have, and that goes inversely proportional to the distance that you are, it goes inversely proportional to this distance. So if the center of the lens is at some coordinate 0, and if you look at some other angle, then the density that you measure goes inversely proportional to the distance or the angular separation here. Okay. So now that you know what kappa is, can you find the lensing potential psi? So because once you have the lensing potential, you get everything. So what lensing potential gives you a kappa of this form? And this is particularly where the vector nature of these angles come in, because if you treat this as scalars, you will be wrong. You will get a wrong answer. Also, so this is a example of a more generic case called axisymmetric lens, because everything here depends on the magnitude of this vector. Nothing depends on the orientation of the vector itself. That's because if you're looking at this sphere and if you rotate it along the axis, it's symmetrical. Nothing really changes. Which is why everything depends on the magnitude and not on the orientation itself. But a more generic, a distorted lens would not have this dependence. So this is a particular case of axisymmetric lens. So let me write that down. So I will tell you what the psi is, and then we will see why treating theta as a vector is very, very important, because we will get very different answers based on whether we treat theta as a scalar or as a vector. So I will write this as a claim because we still haven't proven this. So I will get rid of this proportionality constant by writing it this way. So theta is again the Einstein radius, but that does not matter. Treat this as some constant for now. So this is the claim that I make, and if the lensing potential is given by this, you can use this expression to get kappa, and you will see that you get this. Now let's do it the wrong way by assuming that this is just a scalar, theta is just a scalar. So this would mean sorry, this is not particularly the wrong way. Actually, never mind the wrong way. So the easiest way would be to realize that this quantity or this operator is also equal to so again this is, you can treat this in Cartesian space or in polar space. This would be the this would be the easiest one, but if you are not comfortable with going from here to here, we can just do this in Cartesian space. So I have just written the magnitude of theta, the vector, in terms of the individual components, and theta psi by theta 1 is, we get half so all I am doing is just the partial derivative with respect to theta 1, and if I do this for theta 2 as well, or let me finish the other derivative. Yeah, it's probably easiest to do it here, but we can nevertheless do this. So I have differentiated theta 1 first, and now I will keep theta 1 and then differentiate this. Minus half. I think this is correct. Is this correct? I don't know. Can you also, so you know how to differentiate these functions, right? It can look complicated.